Hey everyone, welcome to this week's question show. I know I'm in a strange location with someone beside me. What's going on? So this is Dr. Pamela Gay, my co-host on Astronomy Cast. And this week, we're in front of a live audience as part of our 500th episode of Astronomy Cast celebration. We're here in Edwardsville, Illinois, and we're doing all kinds of stuff. And one of the things that we're going to be doing is this week's question show for my YouTube channel. I've got my questions right here, and instead of taking them directly, I'm going to fire them a bunch at Pamela and see how she does. So let's get started. Leonard Soderberg asks, can we just run the LHC on full speed for a while and not insert anything? If there's a dark matter particle, the LHC's powerful magnets might just catch some of them, and the detectors might see them, and maybe a few could collide that we could even catch.
Well, the problem with this concept is, as far as we know, dark matter does not interact with the electromagnetic spectrum. So if they're running the magnets at full power, they're running the vacuum at full vacuum, and a dark matter particle happens to wander through the side of the detector into the vacuum accelerator ring O going faster, it's just going to go, yeah, I'm here, so what? I don't care about this electromagnetic thing that you're using. And it'll keep going on its merry way and not care. So best case, something interesting maybe comes into existence and then collides into something and destroys something. And that's the best case. So let's not try this. No.
Right. But the key is that you want to have the vast power, the vast energies put into these particles before they run into the detectors.
Well, so there's a difference between trying to catch a wild dark matter, whatever that particle is, and accelerating it, and doing what we're trying to do today, which is taking known particles of known mass that are known to accelerate when put into a magnetic field, and getting those going faster and faster and faster so that the fullness of their kinetic energy, the fullness of their mass energy can all be collided together, releasing a bunch of energy that is all going to turn into stuff and things. And the hope is that some of these stuff and things that come out of this well understood collision will happen to be dark matter particles.
So there are other detectors, other experiments that are set up to be able to do this. For example, the Ice Cube Neutrino Observatory in Antarctica that's its job, is to quietly listen for particles, neutrinos mostly, that are passing through the detector, but also it's going to be one of the instruments that's going to be able to find dark matter. And so that's what you've got. You've got a whole bunch of detectors in a very pristine environment that are waiting for natural events coming from the sun, supernova, other things. The LHC is not. LHC is equipped to find particles that are running via collision that have been generated by human beings. But one of the things that is interesting is that the LHC has found all the particles that it was expected to find, hasn't found all the particles that it was expecting to not find, has not found the particles that they were hoping to find. Right. And so from what I understand now, they are cranking up the LHC, and they're just going to go after it by brute force.
So we have two different things going on here. So first of all, and Fraser's totally right, we do have things like Ice Cube out there, which are these big vats of stuff that's just sitting there being passive, hoping for an accidental collision with dark matter. And it's from that collision that a speck of light will be given off that the photomultiplier tubes will see, and that is how we might eventually find dark matter, is through that accidental collision. Now, with the Large Hadron Collider, there are all these folks, all these theoretical physicists hoping to discover supersymmetric particles, hoping to find other things that would prove their theories that say there's this underlying physics behind the standard model of particle physics. And they can't find any of their wanted particles for their expansions of the standard model. And I, for one, am completely enamored of the idea that our universe does not have any underlying physics. Right. This goes toward the idea of a multiverse where each version of the universe has its own, well, here is your set of rolled dice, and here's your set of rolled dice, instead of one underlying equation that evolves out to say, and here are all of your particles.
Order of the White Lotus asks, are WIMPs the only viable contender for dark matter?
No, there are more theories than there are theorists, I think.
Right. So what is the leading contender for dark matter that isn't WIMPs? WIMPs being weakly interacting massive particles. So they only interact by gravity. We just did a whole episode about dark matter on my channel. People are really familiar with it. The leading contender, I guess, is gravity, MOND.
I don't know anymore what the leading alternative is. I mean, there's even been, the best description I ever heard was Don Wingent once said, you could explain all of dark matter by throwing one Acme brick in every solar system sized volume of space. So it could be bricks.
Bricks, just one brick every solar system volume of space. Boom, you've got dark matter explained.
Yeah.
Yeah. Where are those bricks?
Well, they're kind of hard to detect.
Right, because it's one brick. What's really interesting is MOND is getting, this idea that we just don't understand gravity. If you just modify the calculations of gravity, and there's some really interesting research, I don't know if you've been following this, where people are studying dwarf galaxies, because essentially, we know that gravity works the way it does in our small area, and we know how gravity with dark matter seems to work at the largest areas. And so there must be some point where it switches from the way it seems to work at the smaller regions to the way it works at the largest regions. And so people have been studying galaxies of different sizes and bringing the sizes down, and they're finding that even with dwarf galaxies, you would expect that switchover starting to happen, and it's still the particle still seems to explain it. Modified gravity doesn't seem to work even at that scale.
Yeah, modified. So the original way that people were formulating modified Newtonian dynamics is you would take the standard equations we have for relativistic gravity, which are basically Newtonian gravity plus some extra terms that help you out in really high mass, high gravity, high velocity situations. Then add another set of terms, which is your modified part. Now, we haven't found a set of terms that works better than the idea of particles, but we know there's something fundamentally screwed up with our understanding. We're just not sure where. And we don't know if it's an observational misunderstanding or what. And the things that lead us scratching our head is we can't piece together why we get different values for the Hubble constant when we measure using more local means and when we use means that look back at the cosmic microwave background era in time. And so this is where you have people going, okay, is it an observational problem? And Adam Rees is banging that with as big a hammer as you possibly can. You have people looking at it from the theoretical side. So this is one of those cases where science is going, we know something's wrong. We're not entirely sure what. We're open to all ideas, but every time we try and just add a new term to gravity, it doesn't work. So we're going to keep looking until we get it, but that's probably not the answer.
Yeah, and I mean, you said there's more theories than theorists. There are almost as many more detectors as theorists. There are dozens of experiments going on in the International Space Station has a detector, the AMS. There's the ice cube that I mentioned. There's a whole bunch at CERN. There's stuff in Japan. There's the snow lab.
But there's still thousands of theorists.
Yes. Maz Oler asks, say you were next to two black holes colliding, what would happen to your body when the gravitational waves passed through you?
I think you'd already be dead and spaghettified and not worrying at that stage.
Right. So gravitational waves being the least of your concerns at this point. But if you were close enough to two black holes colliding or really extreme gravitational waves, what would those do to your body?
Well, it depends on exactly where you are in the interference pattern of the gravitational waves. Depending on if you're just hanging out in a null spot, nothing happens. If you're hanging out in a maximum amplitude place, you might oscillate in size in ways that, well, space-time's doing it, so I'm not sure how you'd feel about it. But this is the cool thing about having this happening is you end up with patterns of waves, and your location determines your fate.
But like when those gravitational waves are passing over us, we are actually getting
Bigger and
stretched
smaller,
out
bigger and
then
smaller.
put back together.
Yes.
And so if you're close enough to one of those gravitational waves, you're going to be pulled apart, and you're not going to want to go back together very well.
Well, you've already. This is one of those chicken and the egg issues. If you're that close to a black hole, you're probably becoming part of the black hole faster than the merger is taking place.
The radiation is already taking you out. The tidal forces have already taken you out. The gravitational waves are the least of your concerns. All right. Mr. Ethanines asks, Venus does not have a magnetosphere either, so why doesn't its atmosphere get blown out to space like Mars?
It's an issue of which atoms are you worried about? Here on Earth, helium is a non-renewable resource, because if a helium atom gets up into our atmosphere, one bad collision with an oxygen molecule is going to send that little helium off at escape velocities to visit the rest of the universe. Now, on Mars, you're looking at an atmosphere that does have like some nitrogen, some oxygen, but those atoms are the heavier ones that are moving kind of slower. You have lots of the various carbon atoms. The dry ice evaporates, becomes part of the atmosphere, and then freezes back out. Those heavier molecules Mars can kind of hold on to. It loses the lighter weight ones. Now, Venus, bigger gravity. And we're talking like an atmosphere made of really massive atoms that are going to require a really big push to get them going at escape velocities. So you have this double problem of large molecules, which have more mass and require a larger push to hit escape velocity, and you have a larger object, Venus being larger, so higher escape velocity. It's just one of those double-edged problems of Mars is smaller, less gravity, and we're talking about smaller molecules that are getting blown away.
And so the only reason that Earth's atmosphere isn't getting blown away is because we have our magnetosphere.
We have our magnetosphere. We're still losing helium. So this is my soapbox. Do not buy your children helium balloons. You're being an irresponsible human being.
Oh, Rock Hard Cyborg asks, is there a way to create an unmanned vessel whose sole purpose would be to basically kick space garbage back into the atmosphere? Meaning space garbage would be disposed of by being forced back into the atmosphere to fall and burn up. Would this even be useful? Would it be feasible?
Yes. Now, the problem is, so space junk is the problem. NORAD, the North American, can't remember the rest of the acronym, is out there constantly monitoring for space junk that's just a few centimeters in size and bigger, and sometimes they're even able to keep track of stuff that's smaller. Because when these things hit your spacecraft, it can destroy your spacecraft depending on where the hit occurs. Now, we have lots of satellites up there that have died over the years. Batteries die, solar panels start doing the thing. They get knocked out of alignment. They're orbiting pieces of junk. I remember as early as '88, NASA was working on testing various spacecraft that would be able to go out, gather things up, either boost them or drop them, change their orbit, and otherwise clean up space. Now, unfortunately, while many of these things have gone through the planning process, nothing has made it all the way through to the we're actually going to build this and launch this. In an economy of limited resources, we'd rather have that space telescope than that, trash collector.
Right. I mean, space junk, if it's low enough, is doing this already. It's already going to be crashing back through the atmosphere. Just give it time. It's the stuff that's higher up that's going to maybe stick around for hundreds and maybe thousands of years that's really the problem. And as you said, there have been plans. You can inflate a balloon on the side of the space junk, and that will slow it down. You can zap it with a laser and remove a little bit of the material, and that will slow it down. It'll act like a little thruster on the side of the space garbage. Or you can go and pick them up one at a time, or even, as you said, give them a kick. It's just every single piece of space junk is on its own separate orbit, and to be able to actually interact with it, you have to put out a ton of propellant to match orbit with it, and then interact with it, and then move to a new piece of junk. And so are you going to launch an entire $200 million mission to remove a glove from space?
You could.
You could. It's possible. But then you're going to have to, crash that whole rocket into the atmosphere, and then you're going to fire another one to go after that rivet. And so at a certain point, it just doesn't make economic sense to do this. Magavartak asks, why are the pictures of planets black and white and not colorful?
Because we want to get as high a resolution as we possibly can with our detectors. And if you want to detect more than light or no light, you need to have, different sensors for each one of those colors. So when we build our detectors, we build them with a whole bunch of little sensors that go light, no light, and then we put a filter in front of that. And the filter says, okay, I'm only going to let red light through. And the detector's like, okay, cool, I'm going to detect red light or no light. We then swap out the filter, pick up the next color, and we combine these different filtered images to create the full color images. But in between taking those multiple high-res images and processing them together into one full color image, each individual image is just counting how many red photons there are, how many green photons they are. And a red and black image looks worse than a black and white image, so we tend to just display them as black and white.
Yeah, they're for science, not to look pretty.
Science.
Yeah. And what's interesting is like those really amazing pictures of Jupiter taken by the Juno spacecraft. Juno's equipped with it's equipped with one camera, and then it has 4 different filters that it can use on that camera. It can use the 3 colors, the red, blue and green, but then it also has a near infrared filter as well. And so a lot of the pictures that you're seeing, they're going to use some combination of those filters. And a lot of times, some of the most beautiful pictures of Cassini were not really what your eyes would see. It was just 3 different shades of infrared where someone has said, this one is red, this one is green, this one is blue.
Yeah.
Those are the colors? Yeah.
So astronomy is all about remapping our universe. Yeah. Some of the most amazing images I've seen take X-ray images and map those to the brightest yellowy colors, take radio, map it to the red, and then have everything else in the middle in the blues.
Yeah. Terry Fitzsimmons asks, during the creation of the solar system, what if Jupiter had gained enough mass to ignite as a second sun? In your opinion, how do you think things would have played out for the rest of the solar system?
We'd have a binary star and move on with life.
But right now, you would have to add another 77 Jupiters to Jupiter to make it ignite as a second sun. So you would be dramatically increasing the mass of Jupiter. So if you turned the mass of Jupiter into a red dwarf star and left it where it was, what would that do to the solar system?
So this is one of those times when I could wildly speculate, but one of the things I think I've said before on Astronomy Cast is anyone who tries to tell you they know how the solar system was formed is probably lying, but they may not know it. Almost every week we see a new paper coming out saying we have seen these observations of a solar system that has started generating planets younger than ever thought, that has started having jets younger than ever thought. We now think that the period of heavy bombardment had nothing to do with the period of time of, at least if you read and believed one paper that came out in the last 2 weeks, had nothing to do with the period when Saturn and Jupiter were busy flinging Neptune and Uranus to the outer solar system. So since we don't quite understand how we got here, I'm not going to say how that would affect things. It would affect things. But, I just don't know how.
Right, but you've mentioned in the past that Jupiter on its own has already threatened to throw Mercury, Earth. Like it's a destabilizing influence.
Us around.
Sure. And so if it was 77 times more massive in that close orbit around the sun, it really feels to me like there would be more mayhem.
But we don't know where it would have ended up because Jupiter didn't start there.
No, but if we just replaced it, if it created again.
Yeah. So if you change the starting conditions,
right,
you change everything.
But there are situations where you can have binary stars with stable planetary systems around them.
Totally.
But they don't look like the solar system.
No, so you wouldn't end up with a binary star system that has planets orbiting one of the stars on the inside and then orbiting the 2 of them on the out. The solar system would be radically different. I'm not going to speculate on how. It would be cool. I'll
But
go
you
with
either
that.
you get binary systems where the planets all orbit, the stars are in a tight binary and the planets orbit around them together,
Yeah.
or one of the stars is really far away and the planets are orbiting one star and then the star is like way out beyond, say, the orbit of Pluto or farther.
Yeah.
Okay. Steve Richard, why did the gamma ray burst reach the Earth after the gravitational waves? If they both travel at the speed of light,
They don't.
you would expect them to be simultaneous, right? Or at least the burst would happen near the end of the wave trip. Thanks for the great video. This was talking about the kilonova event that happened last year, where the gravitational waves and the gravitational waves arrived first, and then the visible radiation arrived about 100 seconds after the
And the
gravitational waves started
neutrinos
up.
were different times.
And and the neutrinos were a different time. And so the question is, if gravity moves at the speed of light, why didn't the gravitational waves and the visible radiation arrive at exactly the same time?
Because the stuff that generated the light doesn't move at the speed of light. We had to wait for the shock wave to propagate out, generate that
Yeah.
light. And so the gravitational waves were one of the first things to happen. And we had to wait for the shock wave to create the light that would then chase down those waves.
Yeah, it's amazing to think about it, is that when you're seeing the gravitational waves, what you're seeing is that final spiral as those two stars are about to collide. That's what generated the gravitational waves, and that's why that arrived first. It was traveling, those waves were traveling at the speed of light, and then those two neutron stars collided into each other and generated the electromagnetic radiation, which then traveled at the speed of light. And here, however many hundreds of millions of light years away, we saw gravitational waves, and then 100 seconds later, or whatever, however long it was, the electromagnetic radiation passing. And so they both were traveling beautifully at the speed of light, with that perfect distance in between them maintained for hundreds of millions of years.
And the neutrinos were not moving at the speed of light. And I don't remember exactly when they arrived, but I do remember it all matched out one of the sets of models. So we now understand where gold comes from and how neutron stars, to first order, we don't know the details, but to first order, how they collide.
Agathia says, Fraser got a question. The theory of everything. Is it going to be literally for everything? As Michio Kaku says, reading the mind of God. It sounds puzzling and somehow close to impossible. Can you share your thoughts for enlightenment? So the theory of everything that physicists are chasing, will it be the theory of everything? Or what is it really going to be?
So let me back up a little bit. Right now, we have the ability to easily, at like the undergraduate level, combine the electric force and the magnetic force into the electromagnetic force. You get a little bit more fussy, start getting into graduate school stuff, you start seeing how you can combine the electroweak force in there, you have the strong force, and then gravity's sitting off to the side going, I won't play. Nope, not going to do it. And you start running into issues like, is gravity strictly a geometric problem? Is it a force that can be conducted by bosons? We don't know these things. And so gravity's just off to the side going, nope, 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 nope. And the theory of everything claims that it can suck gravity in and have this unified way of understanding everything from the earliest moment of the universe, when all of the forces were one single thing and all acted in unity. And so the theory of everything is a way of explaining through particle wave theory gravity, the electroweak, electrostrong, and electromagnetic forces all together. Now, this does not mean it's going to explain why you and your significant other broke up, why my gears on my bicycle stopped 2 weeks ago. It just...
Why some people don't like the taste of cilantro.
Well, that one is genetics.
All
that
right.
one I can explain to you.
All right.
But so the theory of everything still leaves space for chaos theory, which means there's always going to be things that happen that are dictated by probabilities, but we can't know the outcome of a single event. So there will always be unknowns no matter how much we know, and that's kind of awesome. Forsaken
Savior. Fraser, why do people ask you questions that can be quickly Googled? LMFAO. Do you want to tackle that one, Pamela? Why do people ask us questions that they could easily Google?
Because we are their trained monkeys. They're internet puppets, and they like to see us dance.
Maybe. I think it's really important. The problem is that anyone can put anything on the internet. And so if you search for things like, say, the Van Allen belts or the moon landings on YouTube, you are going to get a bunch of answers that are super wrong. And so I think it's really important for people to be able to trust those sources. And I think when we get those questions that people are like, well, you could have easily Googled that. Actually, if you Googled it, you would have gotten bad answers from bad sources that would send you in the wrong direction. I think it's really important for people as they're starting to they want to trust sources on the internet. And it's going to be very much about, do I trust the person? Do I trust the history and the work that they've done to provide a fairly rigorous, well researched, well justified answer, as opposed to, is it some internet silliness, right? Is someone just going after conspiracy theory and things like that? So I actually am honored when people post questions. It feels like that person is trusting me, is casting a vote in my favor as one of the sources that they can trust on the internet. And I, as you guys have seen, I will answer questions all day. Just keep them coming. Bring them. It's my honor and I'm glad to do it. And don't ever feel like you should have Googled it first. Ask questions. I love it.
And one of the things that tells me that people are finally learning to be more scrupulous is I don't know about you, but one of the most common questions I get is, how do you know this? They want me to justify my ability to be an expert on the internet.
Yeah.
And the other day when I Googled about the National Solar Observatory, Sunspot Observatory, to find out what the heck is going on, not that I could, but all of the top links and videos go to conspiracy theories. And this is true a lot of places, because the people like us that want to live in a facts-based universe, we still watch the conspiracy videos so that we can combat them. And then all the people that believe in the conspiracy videos watch them. So they're the ones that get the most hits.
Yeah. It's definitely frustrating to see some of how many hits the conspiracy theory videos get. In fact, there's conspiracy theory videos that take clips from my Guide to Space show and cut them up and then make me look like I'm saying things that support their conspiracy theories, and they get 10 times as many views as any of my videos ever get. So I can see that this is the trend, that someone will say something. There are these channels, and you know who you are, who will post conspiracy theories because that brings in the clicks, it brings in the viewers, and it's this short-lived relationship with these people who aren't going to trust, and there's some of them that will post like the world is going to end, and they just keep updating the date. Yeah. It's the same video, and then they're just changing the date. So now the world is going to end on May 13th, and now the world is going to end on May 27th. And if you look at the comments, people are going, hey, I thought you said the world was going to end 3 weeks ago. And then people realize what's going on. And so it's a marathon. I'm here for the long term, here to help out, here to answer questions, here to keep a scientific basis on what we do. Evolution Inc. If a Jupiter-sized object was to somehow orbit in the Kuiper Belt, wouldn't that be classified as a dwarf planet, seeing as that it hasn't cleared its orbital path?
So Jupiter hasn't actually cleared its orbital path as it stands. Jupiter, at Jupiter's current orbit, has the Trojan asteroids at the leading and trailing Lagrange points. So the current definition has wiggle room in it. And the wiggle room tends to get rephrased as must dominate its orbital path, because Neptune didn't clear its orbital path, Pluto's in it. End of the day, our current definition of planet is horrible. Nobody likes it. No one has a clear understanding of if Pluto should be a planet or not. But setting aside the Pluto is a planet debate, we don't have a good definition. And the current reason that we're not voting on something new, we just had another IAU meeting, is there's an ongoing debate on should we define planet based on the geophysical characteristics or on some other set of characteristics of the world. We keep learning that asteroids and moons and Kuiper Belt objects can be far more geophysically interesting than anything we imagine, far more differentiated, cryovolcanism, underground oceans, and And do we make that the definition? And then we have all of these lumpy dog bone and other shaped asteroids that turn out to be rubble piles. Are we good calling those not planets? So trying to figure out how to codify rubble pile equals not planet, differentiated with cryovolcanism equals planet unless it's orbiting a planet. And then what is the ratio between those objects that makes them a moon and a planet versus a binary planet? It's hard.
Yeah.
We're just not there yet.
And it doesn't really matter.
Just use the word world.
Yeah, I use world. So I just wrote an episode. We have shot it. Chad is editing it about Pluto and about New Horizons. Sort of any new information that came from New Horizons, how it's about to do another flyby, ideas to send a return mission to Pluto, and I double checked, and I didn't use the word planet once in the entire video. I am so not interested in having this conversation and I know the rest of them are too. I know Alan Stern doesn't want to have the conversation. I know Mike Brown doesn't want to have the conversation, but other people have.
Alan Stern totally wants to have the conversation.
Well, he would like it to be a planet again.
Yes.
Yeah. And Mike Brown, I guess he would like to find Planet 9. But the point is, I think that for a lot of people, it's just this emotional reaction to Pluto not being a planet. And the wonderful thing about science is that it changes and it finds new things and it rearranges our understanding of the universe. And we need to be open-minded as these new discoveries are made. That the fact that this is even a debate is because of the wonderful discoveries of an enormous number of objects in the Kuiper Belt. Why can't we just be happy with that? Thanks, everyone, for joining us for this week's question show. We'll go back to our regular format next week, but I thought just because we had Pamela here, it was great. You should definitely follow Pamela over on Twitch and YouTube, and, of course, listen to us on Astronomy Cast. You've got 500 episodes that you can catch up on and listen to. So thanks, everyone, and we'll see you all next week. I might be on a boat shooting the next one. Who knows what happens?
Bye-bye.
See you later.